Good morning! In the last lesson, we introduced the ISO nomenclature of the inserts. We also said that there is a nomenclature for the insert holders. But the definition of the insert is definitely the most important and must be well understood by anyone working in the turning sector. So let's continue with the second part of the ISO insert nomenclature. Obviously, Paolo is here with me, and I am Fabrizio. Let's resume our coding, and let's do it by taking a WNMG insert, leaving blank for a moment the numerical part that follows the letters, which we will see in this lesson. Now Paolo, I'm going to show you 3 inserts, and I want you to tell me which one corresponds to a WNMG. I want to see if you have studied the last lesson. I'll give you 3 seconds. 1, 2, 3. No, Paolo, nope. This is not the right answer. But you were almost there. Number 2 is the right answer, not 3, and I'll explain why. Keeping in mind the scheme of the first 4 letters, let's analyze our WNMG insert. The first letter, W, identifies the shape, which is a trigonal with an angle between the cutting edges of 80 degrees, so potentially insert number 2 or number 3. But the big difference is in the second letter. The letter N corresponds to a clearance angle of 0, so there must be exactly 90 degrees between the face and the side. If you look closely at the third insert, the one you chose, you can see that it does not have a 90-degree angle between the face of the insert and the side of the cutting edge. In fact, the second letter of the third insert is a C. As a result, the second letter will affect also the fourth letter, which will be different, because the relief angle already identifies the fact if the insert is unilateral or bilateral, and consequently, the machining on the insert itself. In fact, WNMG, therefore G, if you look at the scheme, presents a machining on both sides of the insert. This situation is only possible in the presence of bilateral inserts. Finally, a consideration on the third letter, M. It is the same for all 3, since it is the most popular tolerance class, but in any case, you could not have understood it from the drawing alone. So the first insert is an RNMG, a round R shape with a 0 clearance angle, the second is WNMG, and the third is WCMT. Paolo, do you understand now where you made the mistake? What do you mean you were very close? No one remembers a soccer player who was very close to the goal, but only those who score, only those who kick it in. You'll have the chance to recover. But now, let's continue with the nomenclature. Let's take our sample insert CNMG 120408. We have already seen the first 4 letters. Now let's move on to the first of the 3 numbers, parameter 5. In our case, it is 12 and determines the length of the cutting edge in millimeters. So our insert, which has the shape C, has the side of the rhombus equal to 12 millimeters. In the scheme, you will find how the side is measured, and especially the various sizes combined with the shape. So we will not be able to order a C-shaped insert with side 17, but we'll have to change to the larger size with side 19 millimeters. Obviously, increasing the size of the side will increase the cost, so you will have to consider this increase based on the fact that the removal capacity of the insert will be greater in terms of depth of cut. The second number indicates the value of the insert thickness, the amount of which is derived from the inch to millimeter conversion. In our example, 04 stands for 4.76 millimeters. In the case of the screw clamping inserts, which are positive, we would have, for example, 03, which equals 3.18 millimeters. Or another symbol such as T3, which means 3.97 millimeters thickness. Let us make a few considerations on the choice of thickness. Firstly, the thickness called by the ISO table with the letter S is a standard value. Second, the thickness indicates the height of the resistance section. Therefore, the greater the resistance section, the greater the strength of the insert. Third, the thickness of the insert, so its strong section, is a function of the length of the side. The longer the side, the thicker the insert, the stronger the insert. And these 2 parameters will always be related. Sometimes, it is therefore advisable to oversize the inserts in order to have a longer tool life, even if buying a larger insert would mean a greater expense. In fact, with the same chip volume, a 12-sided insert with a thickness of 4.76 mm like ours would not have as long a cutting life as its twin with a 16 mm side and a thickness of 6.35 mm, precisely because of the difference in the resistance section, which is almost 2 mm greater. More than once, I've had to increase the life of the cutting edge while maintaining the same working data, depth of cut, feed rate, and speed rate, and I've done so by using a larger insert cutter, which, despite appearing to be economically inconvenient, has allowed me to increase the available tool contact without affecting other parameters. The last number, in our case 0.8, expresses the size of the nose radius in tenths of a millimeter, so our CNMG insert of length 12 and thickness 4.76 will have a nose radius of 0.8 millimeters. Let's see now some considerations that influence the choice of the nose radius. Number 1. We will use one of the values given in ISO. So for example, among the most used, 0.8, 1.2, 1.6, 2.4. Number 2. The nose radius has a significant influence on the strength of the cutting edge, so a larger nose radius is used for heavy-duty cutting. Number 3. The nose radius is related to both the side length and the insert thickness, as well as to the cutting edge geometry. As the insert size increases, it is recommended to also increase the insert nose radius, in order to better exploit the increased chip removal possibilities combined with a larger insert size. Number 4. For both roughing and side finishing, the nose radius influences the feed rate. And in this case, we can say that the maximum applicable feed rate is about half the nose radius. We will discuss this later in the lesson on feed selection. Number 5. Within finishing operations, the drawing itself will guide us on the values of the radii to be used. The insert radius will also be the value of the radius that will remain on the workpiece and the walls and concave edges. If there is no radius on the drawing, I will have to use the smallest possible insert radius on these edges, which is usually 0.2 or 0.4. With the first 7 parameters, we have concluded the information's always present in the ISO coding of the mechanically clamped insert. As we said at the beginning of the lesson, fields 8 to 11 are additional, and typical of geometries related to insert materials other than carbide, such as ceramic or CBN inserts. To be precise, field 8 indicates the condition of the cutting edge and the presence of honing on cutting edge that increases the cutting edge strength. Field 9 indicates the orientation of the cutting edge, which influences the direction of the cutting. This is typical of Canucks inserts, namely a K-shape. Field 10 determines the size of the honing, which in the example shown here is 1/10. Finally, field 11 also refers to honing, but in this case, it is the honing angle. Field number 12 is at the discretion of the builder, who may use this space to provide additional information as preferred. It is usually used to indicate the geometry of the chip breaker on the insert's face. If we take an insert that in the 4th field has a letter F, G, M, or R, the insert will have a specific machining on its face necessary to manage chip control. Paolo, it's odd that you haven't asked me anything about the strange shape that inserts have on their face. No, it's not a tribal symbol, Paolo. Not at all. They are the result of very in-depth research, and are created to be able to control the chip in very precise fields of application, roughing, and side finishing, and will depend on the material that the insert will be machining. Basically, the Inserts Research and Development Center, after analyzing the machinability of a family of materials, designs the chip breaker geometry to allow machining with correct control of chip formation, and defines the working parameters, depth of cut, and feed rate for which this geometry was designed. So we will choose one geometry over another depending on the material to be machined and the type of machining. If we are going to do roughing where the depths of cut and feeds are high, we will choose a geometry that is suitable for the purpose. But if we use the same geometry in side finishing, we will no longer be able to control the chip. And frequently in these cases, it would create a very long chip wire that could distract us and be dangerous for the machining safety. So it is better to thoroughly study and consult the geometries of your insert builder by consulting their recommendations for use or by using chip control charts. These graphs, similar to the one shown here, indicate the area within which this geometry correctly controls the chip. And therefore, since on the x-axis we find the feed per revolution and on the y-axis the depths of cut, it will also be useful to define the parameters to be applied with this chip breaker geometry. With today's lesson, we have completed the topic of the ISO nomenclature of inserts. Paolo, I know this seems boring, but remember the lesson of the parrot. This is one rule you really need to know, because it is entirely fundamental. Anyone working in the field of turning will eventually have to deal with the acronyms we have seen in these two lessons. To help you familiarize yourself with the ISO nomenclature, you will find some examples of inserts with their descriptions starting from the coding and additional info. Paolo, you have to study too. Then during our course, I will ask you questions. And don't get upset, you know I do it for your own good. We'll meet again for the next lesson, always here on CNC of Course.